Off we go. So we're going to talk about two different topics today. We're actually going to finish the slides for once. Got a shorter set of slides. We're going to talk about something called templates, which is a beautiful, beautiful thing, and it helps us save a lot of typing. We've noticed some, probably by now, we've noticed some things that we could make better, and we'll find a way to do that today. And then we'll talk about stacks, which you already learned a little bit about in your lab, right? So let us begin with templates. Other languages call these things other words. So C++ likes to call it templates, but another language like Java, for example, has the same exact thing, but they call them generics. So you're making a template for code. You're making generic code. It all works out one way or another. But here's my motivation. So let's say we really, I know this exists in the library, but pretend it didn't. Pretend we don't want to use the standard library today. Say you wanted to make a maximum function that works on two integers, right? That's something you'd want to have one day. It's a useful function. It's like you'd program it, right? All right, it takes two integers. It returns back which of the integers was the maximum. So its return type is int. It's going to be like, all right, return the bigger one. If x is bigger, return that one. Otherwise, y is at least as big as x. And they could be the same. It's fine. Else return y. That's a correct implementation for maximum, right? So that's nice. That's okay. That's cool. But then pretend that you wanted a maximum function for doubles, for floats, for shorts, for all those different kinds of integer types, and maybe you made up some of your own because you're working in some weird, bless you, in some weird embedded place. Say you had 100 million different data types and you wanted maximum for all of those. And the code's all the same, right? You still have an operator that's a greater than operator for all these things. You'd just be copying and pasting that code 100 million times, wouldn't you? That's all we know how to do right now. That seems like a waste. There's got to be a better way. So that's my motivation, okay? So even though the code looks the same, the types are different, the things that it takes are different, therefore, like it has to be a different implementation, right? Or does it? Or does it? Maybe we can let C++ handle it. So this is what templates are all about. So the goal is, if the code looks the same but the types change, just make a function that takes a variable type. That'll be fun. That's how it'll work. And we're just going to write one piece of code then that has the same body, but it will work for any type that we could give it, any variable type. Call it T. All right, call it whatever you want. And so essentially we're writing like a little cookie cutter. We're writing a recipe. We're writing a template function that will create, like C++ will make for us when we call it on ints, it'll make the int version. We call it on doubles, it'll make the double version. That's what we want. So we get to use like this maximum function that we're about to write that's supposed to work for everybody. It doesn't take an int, it doesn't take a double, it doesn't return a double. It takes a t. It takes something that's a variable. Any kind of type we could want to give it that has that greater than operator. So we'll call that type t. It takes two t's and returns a t, where t is a variable type. That's what we're going to do. All right, so wait for that. That'll be fun. And you can call it, and you can give it a type as an argument. But C++ can usually infer it, and we've been taking advantage of that secretly this whole time. So now we get to learn how the sausage gets made. So here, maximum. This is a useful thing to want to do, right? So here's how it works. So instead of saying int maximum, int a, int b, how do you do it, right? If a is greater than b, return a, else return b. So that's a correct maximum on ints. Here's what I'm going to do instead. You know what? This code should work for anything that has the greater than operator. So it should be able to take two t's of any type t that has a greater than operator and returns which one was bigger. So it's returning a t. Does that make sense so far? It's like whatever that type was, t could have been int, t could have been double. Technically, it works for strings. Do we see the vision here? But C++ gets confused when you say this, like it's expecting t to be a real type. Like, did you make a class called t or something? We got to tell it, no. This is meant to be a templated thing. T stands in for anybody. So you say the word template. Template. And then in between these little angle brackets, you say class t, like you're declaring a variable where t is a type name, and another way to make a type is to make a class, right? So say that template, that's what you say. Template class t in those angle brackets. That's what starts off, that initializes, that declares the variable t for the duration of this function. That makes sense? Where t is a type variable. It stands in for a type, which is so cool. And now it's happy. It's like, all right, I understand that t could be anything. And that's how that works. So this line introduces It declares a type variable. We've never done that before. It's very cool. So now t could be instantiated, right? We can supply a value for t where t is int, and then we get the max on ints. If we call this function with t being a double, we get a maximum function on doubles. Do you see how we have 100 million different maximums all at once right now? Any questions about that? Because that's magical. That's so cool. And the way you call it is the way you've seen before. You know in your hearts exactly how to call this function because you've been doing it already for different types in C++. Like, I want to call maximum the int version, please. You've seen that syntax before. 42, 43. That's me supplying a type argument. Isn't that so weird and cool? So this creates then the maximum function on ints. Does that make sense? That does it. It finds that one. Though C++ can usually infer what you want. Like if you just give it, I don't know, 3.14 and 2.71. It's like, oh yes, those are doubles. You gave me doubles. You must be trying to call the maximum on doubles right now. Yeah, and so it'll get that one. So C++ can infer that we want maximum double here. So that's pretty nice. So it can usually figure it out for you, but you can also supply it. And maximum on strings for sure works as well. Strings have a greater than operator, so let's do that one. Maximum on string. It can take ABC, BCD, and the one that's bigger, the maximum, is the one that comes later in the dictionary. So BCD will be the answer there. And it does the right thing. So we wrote 1, we got 3. Do you see the magic there? Any questions about that so far? Yes? What do you mean by that? Like the maximum on lists? Well, it all depends on who has a greater than operator. So do lists have a greater than operator defined for them yet? Probably not. So if you implemented that operator, then it would suddenly work. But yeah, if you tried to make some lists or some vectors or something, because that is where you've seen the syntax before, right? Like, all right, list of ints L, list of ints L2. I don't know. Say we've made them. See how the maximum, or just try to call it on L and L2. We're going to get a compiler error, and it's going to complain about what you would expect in theory. Oh, apparently there is a greater than operator on lists. Oh. Nice. I didn't know that. I would expect it to be something like it's going to pairwise compare them. It's like this one's bigger, maybe something like that. But I'd love to know what that is. So let's figure that out. List of int, the bigger one, L3 equals that. Let's for every int x in L3 that we get back. What in the world do we see here? See out x in a space. So I didn't even know that. So that's a great question. Apparently that works. Beautiful. For free? It was the 2, 3, 4. So it's probably going to go and like find the first one that's bigger. And then, so it's kind of like doing dictionary order in a sense. That's what you would expect for a maximum on list. I love that. So maybe that works for vectors too. Cool. So yeah, if you made your own type though, which did not have the greater than operation, you just get a compiler error saying like it's trying to call the greater than operator on your type, and just like go and implement that, and then it would work. All right, so that's all it's trying to do. It's really just copying and pasting this code, and it's plugging in int. It's plugging in double. It's made 4 versions of maximum for us. That's C++ doing that for us right now. So that's wonderful. Any other questions about this one? That's pretty cool. So all right, you've seen mine. You try. Go and make a templated function called double DBL, because you can't use the word double because we've already taken that one. That doubles numbers and strings. So here's what I want you to be able to do. So like call your double function on 2, it should give back 4. Call your double function on the string blah, it should give back blah blah. There's got to be, if you're going to do it templated, there has to be one way to do both of those things. The same code, right? Can you find it out? Can you figure which one it needs to be? So see if you can make a templated function called DBL to mean double, right? Because we can't use the full word double anymore. See if it we'll do both things for you. Try it. All right. Questions about the question? Go see if you can make it work. I'll give you a few minutes and you got plenty of time. Try it out. Let me know if you have any questions. And it will work on doubles too, right? Oh, I wasn't even thinking about that. If you want to, yeah, sure. Let's do the written ice for. I can clear that page out for us if you want to go there. Whee! That is a great idea. So yeah, maybe refresh the page if you're already on it, but it should be fine. Yeah, feel free if you'd like to put it on the written ice page. That'd be great. $243. Another minute or so to try, and then we'll come back. All right, take a few more seconds to press submit. If you're on the written ice page, we'll take a look. Dun, dun, dun. That one's good. That one's good. I don't understand the problem there. That's fine. I need to mark those on red. All right, let's see what we're thinking. I need to get back to my, where in the world was I? There. Cool. Look at us, some of us did it. And that is right, it's going to be with the plus. Can't do the multiplication on strings unless you implement that operator, I guess. But the plus just would be like thing plus thing. It will work for both different kinds of types, wouldn't it? All right? Does that make sense to us? So that's going to work, and I'll show that to you. Do make sure to do attendance if you have not yet. I will stop that the next time I remember. So yeah, something like this. Like template, and the name of your templated type. You gotta say template, and this is the setup. Template class, and then you put some word here. Usually, like the people like to do capital letters for type names just to differentiate it from, because usually we use lowercase names in C++ for like int and double and stuff. So you could say T. That's what I'm used to, like T for type. But you could be using anything here. Call it U. Whatever you need here, as long as you're consistent. Like that's your variable type name. Use that everywhere now. Like that exists. And then it's like, all right, it's called double. It takes a T, call it X, and it returns a T. Okay? And the way to make it work for both integers and strings, they both have a plus operator on them. So if you want it to work for both, you need the same code, return X plus X. And that would be the implementation. And that's what they have in common. Any questions about that? Do we see it? So it would be happy, and that should do it. So that is a templated function. You know, because you've used lists and vectors and things, that there's more that you could template. You can make templated classes, couldn't you? So are we ready for that? All right. So do shout out if you have a question, but let's make a simple kind of class that like adds some stuff. So like you know that it is okay. It makes sense to want to make a class sometimes that doesn't really care about the type of things inside of it. Like you got a list, you should be able to make one list implementation, one vector implementation, because all it is holding an array of whatever that type is, right? That's all that you care about. You're not really using any like integer specific things if you're making an int vector like you did in your lab. It could have been a string vector. It could have been a double vector. So it should have been templated probably. All right. So we don't care about the types. It works the same for any type. Let's make a templated class where the implementation just happens. All right. So let's make an adder class. It's silly. It's just it's gonna take two member variables of a certain type that can be added together. So of type T, X and Y we'll call them, and then we'll have a method that is called add that adds the two things together, and like that returns back their bigger thing. Okay. So let's make a header file for this little adder library. We'll call it adder.h. All right. And sorry, not that one. Remember your header file guards. And let's see. Well, it's going to be called class adder. Think about it. It's going to take two things, right? It's going to have the for the member variable, I'll just keep everything public. It's going to have an X and a Y, the two member variables you want to add together. It's silly, I know. And then it's going to have an add method that adds the two things and gives back their sum, I guess. And I guess it can be const as well. But like, do you see how this is a class that has some member variables and does some work on things of, like, it should work for any type that has the plus operation, yeah? And that's why we want to template it. So again, for the same reason, you're going to say template. Like we have to declare that T so that C++ is not confused about it being like, is that an actual type you want to use, like that you didn't declare somewhere, that you didn't create? No, it's a variable. So class T, and now it's happy. It understands that adder, all the T's inside of there are variables. Okay. Any questions about it so far? So it's meant to just, you set the member variables and you call add. And it should work for anything that has a plus, because that's how add's going to be implemented. So that's how I want to use. Here, let's go to like the main. Let's make we'll make like a adder main.cpp file that includes our little library. It's like include adder.h, and it makes like an adder on ints a, and like it sets a's x to be 42, a's y to be 43, and it's like cout a.add. Add those things, please. Like that's how I want to use it. It's silly, but I think you get the point, right? So I could use it on ints, I could use it on strings. make another adder called, I don't know, adder B. And its x and y can be, I don't know, the string 42, the string 43. Oops. And then it's b.add. So like it should work for both of them, and it's going to be adder on strings this time. It should work the same, yeah? If that's what I want. Questions about that? If that's what I'd like to be able to do. And so I need to give an implementation just to the add method, like that one and for all, give it once and for all, and C++ will make the versions as I use them. That's kind of how it works. This is the one time where you can disobey the rule of making a separate C+.cpp file for your library. This is the one time you do that for a very weird reason. All right, so you cannot have a .cpp file anymore with the implementation of this add method. The second you use templates, it's not actually code that we're writing. We're writing something that could become code. So it's a little weird and meta. So here, when you have templates, what's going on is, let's go back to our original example. That makes more sense. When you make this maximum function, if I never called it, this maximum function does not exist anywhere. It's not a real function when you make a template. Only when you use it does C++ like copy and paste it and put the right types in and make that version. So it's made 4 different versions of maximum because I use it with 4 different kinds of types. But if I didn't use it at all, it would not appear anywhere. So like the code doesn't exist until you use it is the idea there. Does that make any sense at all? Like that, it's just going to copy and paste it and like put the right types in when you use it. So it's not real code in the header file because it would make no sense to separately compile this adder class because I never used it anywhere, so it will become nothing. That's kind of like if you separately compile it, you haven't used it, you've just like given all the definitions, right? And that's the problem. So with the template, it doesn't exist until you use it. So you got to put the code right here because it's going to be the main program that includes this that's going to make everything happen. So let me just do that and then we'll talk about it. So I'm going to put the implementation here now. That's the moral of this story. And every time you say T outside of anything, like it's just like a method now, you got to say that it's a template again. Like, oh, no, that T, it's a templated type. And this is not just adder's add method. It is the adder type specialized to the type T's add method. You have to be very, very precise because that's how you would have made this adder, right? It's the adder on T's add method, and that's the one that returns a T. Does that make sense? It's a little bit, it's got to be qualified like that because like that's how you would have made an adder over here. Yeah. No, sorry, it's not called add, it's called adder. Excuse me. Got ahead of myself. Well, now it's probably more happy. There we go. So like that's how you would have made the thing. So like it's an adder on T's add method. Okay, that's how that works. And then how do you implement it? So return your x member variable plus your y member variable. That will work for any type T that has a plus. Okay, so we're putting this in the header file. That should make you feel uneasy, and we kind of have to. You could have made a separate CPP file as long as you then went and said include adder.cpp so that it eventually did become copied and pasted into the header file. Some people do it that way. I think that's kind of silly. So we'll just keep it all the same. So let me try and explain this in comment form. Like I'm just going to say it a bunch of different ways until it makes a little bit of sense. So the implementation of a templated class cannot be compiled separately. Can't do the -c on this because you have not actually used the thing, so it's not going to make any real version of adder. So the reason why is because templated methods / functions aren't actual code. Until you use them, they do not exist. It's only going to make the ones that you use. So that's therefore the work is now shifted to adder main because that's the one that includes adder.h. So this code is all being copied and pasted right there. So now it exists, and right here on this line is where the adder on int type got made. Does that make sense to you? That's the secret there. So like it needed to, like that, it's the very circular thing just happened. We had to go from here, it got included here, And only now, when we're compiling attr, just attr main is the only file I need to give to G++, because it's getting everything that it needs from this header file. Right here is where attr on ints got made. It copied and pasted it, made all the right versions of everything. And right here is where attr on string got made. It copied and pasted everything, made all the right versions right the second I said that. All right, and that's how it's getting compiled. So I only need to give one thing to G++. I don't need to compile anything separately. It's just like the second I use it, it's happy. Okay, and so I think that's all that I really wanted to say. So it's only attr main that I need to give and compile. There's no other CPP file. Oops, attr main. Cool, and we get our what we expect. 85, which is the int sum, and 4243, the characters sum for the attr on strings. Okay, so it's two different things. Same class, though. It worked differently on the different types. As long as they had a plus operation, it was able to make that type that we needed. And that's the full definition. Any questions about any of that? It's just weird syntax, but I hope you see the point of it. Right? It's very, very useful. You don't have to make a bunch of different versions. Like, you would want to do this for your vector class for sure. That's what C++ did. It's great. So yeah, I have a whole slide now dedicated to everything I just said. Let's go through it one last time, and then we'll get to other things. So okay, when you make a templated thing, you can make a function, a class, whatever you need, something with code inside of it. It's not really code yet, right? You have to call the thing. Just like for maximum, that's the best example. You've said how to create a maximum function should you ever need one for any type that has a greater than operation. So it gets translated. The fancy word is specialized for the type that you are trying to use it on right now. Becomes specialized on ints, specialized on doubles, the second you use it. All right. So if I didn't call maximum, like if I didn't use it in main here anywhere, maximum would not exist. It's a ghost right now. Only when we use it does it become concrete and into the world of our program. And that's how it works. So secretly, it really is doing this painful thing that we didn't want to do. It is copying and pasting it. The second you use it on a different type, it's going to make that version. It's going to, like, your code, like the executable file will become long because it really is making all those different versions of that function. So they need to be separate in machine code land. But you don't have to worry about it. That's the difference. It's better for us for that reason. So under the hood, it really is copying and pasting the code, replacing it with all the correct types. You would get those 100 million maximum functions from that example if you used that maximum function with 100 million different types. You would get that. It'd be a very long program, very like a gigabyte for your program or something. But they're just going to be made for you, and that's the trade-off. Okay, you still need the code, but we're handing that problem to C++. Like, it's more conceptually easier to just write one, have it make the rest for us. So same with that and our attr class. Okay, so yeah, that's pretty much all that I wanted to say. Are there any questions about any of that? Or I show you a slightly fancier example that kind of goes back to the idea of linked lists. All right, so let's do this. It's fun. I'm giving you part of your lab. You're welcome. So you can have a templated type, right? We've seen this templated list, templated vectors exist. Now you know what all that means, which is great. Whee! So I'm already at the list type apparently. Also, why is this not? I'm unhappy about that. There we go. Like, vectors are templated, lists are templated. Whee! So now you could read this. There's actually another thing in the template type thing that's that has a default that we don't really care about in this class, but you understand how to read that now. You can have two different type variables, and default things. So yeah, let's kind of, you see how that's being declared, I guess. That's how the standard template library does it, and it all works for any kind of type. It's got, like, if we did a push front just like they did, it is a templated thing, and they've made an alias for the type. They've called it the value type. That's what they're calling their T. So whatever that is, that's your value. That's a type of things in my list. Value type is what they're calling it. Okay? It's an alias of the first template parameter, which is called T in the definition. Ooh, it's all making sense. It's all there. All right? That's how it works. So let's see. What else do I want to say? Here is, by the way, oh gosh, do I want to show that to you here or there? So yeah, that's what they did is they made an alias. So they said value type, that's going to be the same as my t right now. Like that's, I can just use both. You can make a second copy of a type to give it a new name if you want to. And the way that you do that is with a type def. If you'd like to do that, this is how it works. You say type def, the original name, and then the new name you want it to be. So you can look this up more if you'd like. But like if you have node of int and you know you're going to use that a lot, but you really don't like pressing the shift key a lot too many times, you can say like, all right, type def node of int, let's call that int node. That's easier for me to type. And so every time you say int node now, it's going to be like the same as this. Those are the same type now. That's how you make an alias of a type. So they did that in the STL, but you can do it too. All right, what I'd like to do then is I'd like to make a templated node struct. I'd like to do exactly this. I'd like to make a linked list node type that doesn't depend on the thing inside of it. Like it's a linked list of, it's a node that holds ints as data, a node that holds strings as data, and yet like you can make a linked list of ints with nodes of ints, or you can make a linked list of strings with nodes of strings. Like that's what we want to be able to do right now. So let's make that happen. Let's make a little templated node struct with a templated push front function. So this is not giving away too much of your lab. It's going to be function based for my example, but you can extrapolate to turn that into a method, right? So here's what I want to be able to do. So let's see. I've got, how do I want to do this? I've got a linked list, and I am representing that with a first and last. So here's my first, here's my last. That's exactly how you're doing it in your lab, right? And let's say maybe it held the list 1, 2. So it's a list of ints this time. I want to be able to do this. This is what I'm going to make for you, and it's going to be a templated. All right, I want to be able to make a templated push front. I'll make a function for this example, but you can probably use that pretty well. I'll make a push front that takes first and last, and the value that you want to push to the front, and like that's how we're going to call it. And it will understand like, oh, I need to work on a linked list of integers, then it's push front for int lists. We'll deal with that in a second. Then our job then is to like, first step is to make the 42 node, right? Mm-hmm. And then we should make the 42 node. Step 1 is to use the old first, to make that its next. That's step 1. And then step 2 is to chop this off, and now the first is that thing. That's the order, because otherwise you would lose where this first node was. Yeah. So that's going to be push front. Let's get started with that, and we'll come back, because like it's going to be an interesting way to give those parameters, because we have to be able to mess with first, don't we? We have to reset it, potentially. So the type of first needs to be a reference, but first is already a pointer. It's got to be a reference to a pointer. It'll look a little weird, so we'll get to that. So yeah, where I want to go with this is push front.cpp, and so I would like to make a templated node type. So I want to say struct node, and instead of like int data and node star next, like that would be a linked list on integers holding integer data. Like you've programmed this enough by now, or you've seen it enough by now to know that that int didn't really matter, right? It could have been anything. So this should have been a templated struct. You could have said t data, or just to get practice with other things, we'll call it u this time. So like, all right, template class u. So now this is variable, and I need that semicolon, don't I? And now this is a node of any kind of thing. Any kind of thing you want to supply for you, that becomes a linked list on those things. So a node of ints will hold int data, a node of strings will hold string data. You have all those things available to you, okay? So here's how I want to be able to use it. And I want to make a push front, right, as well. We'll get to that. But let's make like an empty list of integers. How would we do that with our node struct now? Make an empty list of ints. How could I do that? Well, I'm going to say node of int star first equals null. Node of int star last equals null. And this could have been anything, and this could have been a linked list of doubles by just saying that. Does that make sense? That's kind of what you want. It should be templated. Like the implementation doesn't really care about data, the type of data, just like it works the same. You can get it out if you want, but like that works the same for any possible type, doesn't it? So that's what I want, and I want to be able to push front, the int version for int lists, please. First, last, and like 3, 2, 1, and that will make the list 1, 2, 3, right? And then I want to be able to go through this list after I make this push front function and say like, all right, let me iterate for every node of int star n. Start that at first. Keep going while it's not equal to null. N equals n unknown x to advance it. See out. N's data, whatever type it was, it's ints, we know. But it could have been any other thing, as if you changed what was there. Change it from int to something else. It should work the same. And that's where we're going. Are we ready for the definition of push front? You see the vision here? Like this could be anything now. Whatever you want to put there. All right. So let's implement push front. And for reasons, I hope you see that if I'm passing first here, first sometimes needs to change, yes? I need to mess with its value, and whoever, like, that needs to affect the original first variable, right? Because the first of the list has changed now. So I shouldn't be getting a copy of first, I should be getting a reference to first. Does that make sense to us? If this is only a function. So if it was a method, you could, of course, change your memory variables. But this is being passed to me. I need to be able to mess with first. It's not the same first anymore. It was this, now it's this. To make that change and have that affect the original first variable, this needed to be a reference parameter. Does that make sense? Yeah. You see it? That's very important. And for the same reason, actually, last needs to be a reference as well, because what if the list looked like this? You know that sometimes for push front, even, you needed to set last, because if it was empty initially, right, the very first node, if this was 42, like we call it when the list looked like this, you got to make your 42 node. I'm going to make it a bit bigger. Make your 42 node. Set the next to be the old first. That works out still. Set the first to be the new node. That's still fine. But then you got to notice that last was, oh, that was null. So that must have been the first node in the list. So the first is the last. So again, we need to change a variable from main's perspective. Like the thing that we passed here needed to have been affected. And we need to make that change for everybody who's using this variable. So I should have taken last also by reference. Okay, so I want to be able to change both of those things. So they need to have been reference parameters, but they themselves are pointers to nodes originally, right? That's the type of first and last. It's a pointer to a node of ints, because it's a linked list of ints right now. So let's work with that. Okay, so here it's going to be called void push front. It's going to take a node of t. Let me do it without the parameters, the references first. Like it's going to take a first and a last. A node of any possible type, right? This should work for a linked list of any possible type. So it's taking nodes of t's, and we're trying to push to it some value of type t. Yes? That's the first thing. Do we see that, first of all? Like those are the types of first, last, and the value you want to add. If it's a list of any kind of type, and it's a variable type, that's how we'll say it. And we'll say template class t to declare that t as a variable type. So that's important so far. But right now, I cannot change first and last are copies. They're just addresses right now, yes? I want to be able to affect, right? First and last should not be like, if I use this function right now, first and last will never stop being null. Does that make sense? First and last from main's perspective will never stop being null. I can't say first equals something and mess with this one unless it was a reference. Yeah? Or you could have done this. You could have done a double star and then passed the address, because that's what a reference is secretly doing, but I don't want to go there. That's too much. So instead, I would like first and last to be references to what they are. Their original type is a node t star. I want the reference version of that. You've never seen this probably. I want the reference version of that. This is a great way to introduce a lot of weird syntax at once. All right, so here, let me try to explain that. Node t star reference is, you read it backwards, right? You always like to read it backwards. It's like this, before that, it's like, this is a pointer to an integer node, a kind of a linked list node on ints. You read it backwards. This is a reference to a pointer to a node on t's. Okay, so it is a reference to a pointer to a node t. So a node type with t data, okay, because that's where we use that variable. And that the whole reason we did that, because we might need to change the values of first and last. We always need to change first, but sometimes last also needs to change. So that's why we did it like that. So now first and last, because we pass them in this way as references, if I say first equals something now, da da da, I'm actually causing that effect to happen to the original main's first variable, which is important because it needs to always track the start of the list. It really is going to do that now. Does that make enough sense? This is very weird syntax. Are there any questions about it? It's just something to let sink in, probably. But now I'm able to do this and cause that effect. That's the whole point. So, okay, let me implement push front for you. So we've got these two cases. Either the list was initially empty or it was initially had something in it. Depends on if we change first or last. The rest is the same. So let's do these first two steps and then we'll look at last or something. So, okay. We always need to make the node first, right? That's the very first step. So let's make a new node specialized for t's on the heap. New node, I'll call it new node of t's. Okay, so it's a brand new node that can hold t data, which is perfect because I have a t value. All right, so if this is very complicated and weird for you, just imagine that this was something you knew about. Imagine that t was int. Imagine that this was a node on ints right now. I'm messing with that. You can hold int data. All right, make it concrete in your mind. And then like, okay, I need to, all right, if I was past 42, that was my value. That needs to be shoved into the data part of this node. So, okay, new nodes, because that's what I called it. New nodes data is that value. That's the very, like, this is step 0. And then step 1 is the next of that new node needs to be the old first. Because that's going to be now the second thing in the list. That's the thing after the new first thing. So the next on that new node is going to be the old first node. So it will turn into the second thing now. That's the thing after this brand new node that's going at the front. And now I'm good to change the first. First is, that's step 2, right? First becomes that new node. That's where it lives now. New node. All right, so that's steps 1 and 2. That's this drawing down here so far. Does that make enough sense? You can more or less steal that in your implementation of your lab. That's the start of it. We still need to account for the potentiality of the list having been empty, right? So that's the last check. So if last was null, this was the first node. So if the list was empty, we need to change last to, so we can check for that by, we set first, if last is still null, it was null from the start, then last is also that new node. It's the one node in the list, so it is the first and the last. Okay, and that should be how it works. And if we did this right, starting from an empty list, adding 3, 2, 1 to the front should have made the list 1, 2, 3. Yeah. I highly encourage you to play around with this, change into something else, and watch it work exactly the same. Because it didn't matter. So whatever you're putting in there, you can get it back out. That's all a list is. Didn't really care about what was in there. It doesn't work in any different way, conceptually. So I get my 1, 2, 3. Beautiful. So here's the struct definition. Again, variable kind of thing for the data. And this is a push front that works for any kind of node with any kind of data in it. Because it's all the same. Like you're just putting it there in that node. Whatever that data value was, whatever type it was, as long as I can copy it. I had a copy constructor, right? I can put it right there. Beautiful. Yeah, that's more or less all that I wanted to say about this example. It should be helpful for your lab. Any last questions about it? All right. Remember, I'm not testing you on this. That would be evil. Sorry to blow your minds 2 days before the test, but this is useful knowledge. We need it. So, all right. Are we ready for a completely different idea? I want to talk about stacks, which you've used a little bit. We can stop talking about pointers for a second. All right. So the stack abstract data type is, you've used stacks, right? You've used the C++ stack one. Do I want to go there right now? Sure. Stack is a container. It can hold things. It has push and pop and like empty kind of. Push and pop and top and size and empty. All those things. That's what stacks can do. You push things onto them. You can pop things off. That's the metaphor. Let's figure out how to build one. We can build one out of linked lists. That's going to be the easiest way. So here. By the way, there's something else that we know is called the stack, right? There's going to be a stack abstract data type with all those operations, right? Because it's defined in terms of operations. We also know about the runtime stack, the functions that are being called and returning. I've always drawn pictures like this, right? Of that, and hopefully your 40 professor did the same. So like main is the first function, then the next, if main calls foo, you draw it like this. That's new work being pushed onto our stack of work to be done. And that's also how foo knows to return back to main. So this is the person beneath you on this runtime stack, this function call stack. If foo calls bar, it looks like that, and then bar returns back to foo, its job is done. Foo returns back to main, its job is done. Now we're back in main. So like that kind of thing. That's what stacks are. That's what stacks are. It's just a generalization where you can, instead of adding functions onto the top, you can add data and make a pile of data. All right. So here's the silly example, and so maybe some motivation. So let's say, I don't know, it's your job to wash the dishes after dinner tonight, and you have a big family, and they're gonna stack up their dishes. All right. And they add more, right? They add more as they finish. So, are you going to wash this dish first? That would be a very bad idea, right? That would take longer, first of all, and then you'd probably drop things. So you're gonna wash this dish first, yeah, the one on the top. That's how it would work. So you're always kind of stuck washing the first one, then you take them off, you put them on the drying rack or whatever. This process sometimes happens in real life for other things and for code. All right, it makes sense to want to do this and code up this idea of like, all right, things are being added to the top, deal with the top first. That is an idea. Okay, so that's where the stack ADT shines. Like, you give just as many operations as you need to get the job done and no more. That's what a stack is. Because I claim that we can implement it with a linked list, so we could have used the list ADT for everything a stack could do, but that gives us more power. We want to restrict ourselves as much as possible when we can, and so that's what the stack is all about. Okay, so here are the operations that you should want to do to a stack. So I'll use a stack of ints. It's like you're adding data. So you want to be able to check if your stack is empty, like initially, right? Your stack is empty, you've got nothing, no work to be done, no data there. When you push to the stack, it's a matter of you pushing something onto it, it's getting loaded to the top, you add the thing to the top of the stack. So let's say, I don't know, you push a value, now you push the value 5, now 5 is the one thing on the stack, it is the top of the stack. You push again, you push the 42, let's say, now you have a stack holding 42 and 5, and 42 is on the top. All right, there's always a concept of where the top is right now. So that's where the top is. So you should be able to go to the top and get the last thing that was pushed. That's the thing that you should always be able to do. That's an operation. So be able to push, add a new thing to the top, new data value to the top, get the top thing, and then pop is the opposite of push. It removes the top value. So if I were to call pop right now on this stack, it would get rid of the 42, it would go away, and now the top would be looking at the 5. Okay? So it's like the 40. I should be erasing this, but I'll keep it there so that you can see it. Okay? Some people disagree about what pop should give back. Like, is pop a void method, or is pop a method that gives back the value that you just got rid of? There's two competing schools of thought there. So I think in C++ land, pop here is void. It just gets rid of the thing. If you wanted it before you got rid of it, you should have run top, I guess, to get the thing back. Get the old top before you popped it. But yeah, pop gets rid of something from the top only. Okay? Does that make sense so far? It's a very simple idea, I would think, because we've seen this before. It's just like you're pushing and popping data, and you can only access a thing on the top. Okay? So that's what a stack is. That's the ADT. That's the operations, and that's how we think of it. We can draw a picture of it. But you can implement a stack. You could implement a stack using a list if you wanted to get concrete, couldn't you? You can make the stack class. Could be templated because it works for different kinds of data values. It's fine. Does the same thing. It should. You can use a list to implement a stack because we know it's very easy to put something at the start or the end of a list, don't we? So that's how we can model the idea of a stack. So let's say that I've got, I don't know, let's say I've got the stack 42 at the bottom there, then I push 7, then I push 3. So you have two competing ways of pushing. It's like you can say, okay, pushing to a stack means I'll push back to the end of my list or push to the front of my list. It doesn't actually matter. So this could have turned into, like if you said that pushing, because we pushed the 42, then the 7, then the 3, pushing was push back to the list. It would have made this list. 42, then 7, then 3, and that's your list so far. Or it could have made, you could have said that pushing to your list, push, would have done it to the front. So like the very first time you pushed it was the 42 node. That was the end of the list. Then you push 7, it pushes to the front of that, if you want to model it like that. Then you push again, you push the 3, and it goes to the front. So you could have done it either way, as long as like you consider the top to be the first thing in this case or the last thing in this case. So it depends on how you did it. Either way is fine. And then if you added a new thing, right, where would it go? You push a 4. For this one, if you're pushing back, you'd put it here. But if you were pushing front, for this one, it would be here. So it's up to you. You could have done it either way. It doesn't matter. Does that make sense? It doesn't matter, but kind of maybe it does. I will. I'll ask you about that. But let's see. Yeah, that's pretty much the answer. If you want to implement the push on a stack, you could use push front, or you could use push back. Do I want to do anything about that right now? No, we'll go to the actual implementation later. But yeah, that's pretty much this drawing. If you want to push to a stack and you're going to implement the stack ADT with these operations, you could use a linked list of ints for this example deep down, and you could either say push front or push back as long as you are consistent. All right, so either way it's fine. You can either add your node at the front or the back of the list, and just remember that your top is at the back if it was push back. Your top is at the front if you're using push front. Okay, so that's pretty much it. Are there any questions about that? Like, that's how you could have implemented it. That's how you could have made a stack. So you're kind of restricting operations because you have a linked list deep down, which you know you can talk to both ends of. We're giving up one of those ends to make it slightly less difficult to use and also slightly less easy to mess up. Things that work in this way. Okay, so that's kind of the philosophy of it. But with this in mind, if this is how you're going to implement a stack using a list as, and you're just going to push to add stuff. Oops, that's not enough. Again. Here is my question for you. Whee. Here is our stack implementation. You could do it either way. My question for you is, what is the worst case running time complexity of pushing to a stack if you're going to use a linked list? All right, assuming that you're using a linked list as the underlying representation, let us go, please, to the by clicker page and do attendance if you haven't already. I will stop that. But please take like a minute or two to think about it, because if you're going to use a list and that's the way you're going to implement it, what is the running time complexity then of stack push in the worst case? All right, if you choose the best kind of implementation, though, so like optimal implementation, but worst case of that implementation. Does that make sense? And that is my question. So give that a couple minutes. Discuss among your neighbors, with your neighbors. Another minute or so, getting your answers. Yeah. All right. Let's see. Let's see what we're thinking. I'll give you another 2 seconds to get an answer in if you want to. Cool. And I also promise to stop that. Look at us. We think with, not a majority, that it's A, but the next most populous option is C. So is it linear? Is it constant? Let's think about this. Because it actually does depend on which implementation you use. So if you use the best implementation, the answer is going to be constant in the worst case. Right? So A is the correct answer with that in mind. But it could be O of n if you did something. Does anybody know what that something is? Yeah, singly linked list and then pushing to which end? Yeah, because we're going to have some trouble. Let's see. Actually, for us, it's not actually going to matter for push. It is actually always constant, even with the singly linked list, isn't it? So like it's going to be constant because front versus back for pushing were both actually constant, but popping, there was a problem with one of the ends for popping, wasn't there? And so if you use push front, that means your popping becomes pop front, right? That's the quick one. That one's constant. But you remember that for our linked list, for our singly linked lists, pushing to the back is still constant. That's still fine because like the next thing is null. You don't need to go find the previous thing or anything. You have it. But when you pop the back of a linked list, if push back becomes your push, then pop back becomes your pop, and then now you have a linear time pop. Does that make sense? So actually, push wasn't ever the problem. Push was always constant, but maybe you're thinking about pop. Okay, so that is the unfortunate thing. And so there is a best. If we're going to use this kind of linked list with the singly linked list with only the next pointers, we should be doing push front and not pop, or push front and not push back, because we will want to eventually pop. Okay, so that's kind of how it works. So let's do how do I want to think about this? So yeah, we did that one. Yeah, doesn't matter for front versus back for push, but for pop is very unfortunate, right? Because if we did it this way, if we did the list, boop, 2, or if this was our stack 2, and then we push 1, and we push front for those nodes, so that was 2, then we push front to our list 1, and then we pop front for lists, that's very simple because we just like remember the next pointer for a split second, like set the first to this next thing, we're good, and now we're good to delete this node. It's always constant for popping front of the list, popping the front of the list. That's fine. That's always constant, but it's not true for the opposite side. Right? Pop back is bad. So here, think about a long list. Let me move it over so I can add some more nodes. Think about a long, long list here. Remember the algorithm for popping the back of a linked list. It's disgusting, right? So you have your last pointer. That's all you got. I need this to become the new last. I have no way of getting there unless I go from the beginning, right? So we are stuck with that in mind. Popping that is very difficult. So we should choose, if we implement a stack using our singly linked list with just next pointers, we should push front for our push operation because that forces us to pop front for our pop operation. And we got constant time for both at that point. That's beautiful. That's as good as it could be. All right. So I hope you see that trade-off being made there, and that makes sense to you. If you had a different kind of list with previous pointers, you're trading space for time at that point. Then it would work at either end. It would be fine. Then it would become constant for pop back, but we don't need to get into that. You'll read about that, right? So that's that. Does everybody understand the implementation and how you would do it? I think you can probably very easily see how all of these operations correspond to their equivalent linked list operation. Yeah. So that's how you can implement stacks. And again, we are limiting ourselves purposefully there. Like you could have, like, why not just use a linked list for what you're trying to do here? No, we're trying to restrict ourselves to just these operations. We've noticed that we can get away with just those, and that helps us in a way. That helps us make the problem simpler and not mess up by accidentally pushing to the wrong side or something. Okay? That's very important to restrict yourself as much as you can. That's also the reason we have classes and public and private, right? Public stuff for the user, just give them the bare minimum of things that they could hopefully not mess up with, and then the private stuff is just for us. That's access is very important here, and sectioning it all off. So there's that. And then finally, a cool little acronym that is very important to learn about stacks is that they're called LIFO. They're last in, first out. The very last thing you put into a stack is going to be the very first thing you get out of it when you pop it. All right, so that's an acronym. We'll have another acronym that is kind of the opposite of that when we talk about queues. So look forward to that. So like that's what LIFO means. The last thing you put in is the first thing you get out. So like if you had this stack, you push a 4, and then you push a 2, and then you push 42. It's like that's your top now. Boop. And so that was the last thing you pushed. The only thing you're going to get out now is the 42. You have no access to the 2 and the 4 underneath you until you pop. Okay, that's what LIFO means. You can't get here, can't get down here anymore unless you start popping. Unless we pop. Okay, and I hope you see that. So you got to get like the last thing that was in is the first thing that's coming out of it if you want to get and move down to the pieces below it. Okay, so that is what LIFO means. Does that make enough sense? Just an acronym. Question?
Well, what's the point of a stack if you can only ever access to the thing on the top?
Well, it's the same idea as like modeling this idea of like you're washing dishes. It does, sometimes it only makes sense to work on with the topmost thing. Like let me try to think of a good example. Have you ever gone to Wikipedia and you've gone to, what's today's thing? Today's featured article is a stratovolcano, cool. And you've gone like, okay, magma, what's that? Gas bubble, igneous rocks, those look cool. You're kind of pushing to your stack of things I want to look at right now. Does that kind of make sense? Like your tabs become a stack at that point. And then as you close them, okay, I learned about that, I'm done. Or, oh, I have another thing I want to learn about. You push that, and you look at it, then you pop it. So kind of like your browser history in a sense is a stack. You can think of it that way. But there's real life things that you would want to do that are stacks. Another good example is like your settings app of like a phone. Like if I go to my general information about you're pushing new pages to the stack of places that you've been. And when you press the back button, you're popping that, getting back to the previous window. Does that make sense? Something like that. So that's where you'd want to use this kind of thing. You don't need any other ability on a linked list if you implement it using a linked list. That's a great question. Yeah, I hope that kind of motivates it a little bit better. Yeah, that's what stacks are kind of for, in a sense. Any other questions about any of this stuff? Just a few more slides for the day. Might as well go to the C++ standard template library implementation. We'll have just a silly example. You know what it does now. It is going to be implemented using more or less a linked list. And the documentation says that. So let's make a little example of a stack after looking at the documentation. How about that? So here, I've already gone to it. Nice. It's a container stack class. And you can click like on the constructor and like you can see all these different things that you can do. But the constructor usually has a good example. It's like, all right, here is a stack of ints and, oh, they're not even calling push. Never mind. Go to the push example. Like, okay, it's pushing a bunch of numbers onto the stack and then it's popping them as long as it's not empty. That's a very common way to want to iterate through a stack because like you go to the top and then you pop it. And then as long as it's not empty, you can get stuff off of it. Like that's your condition for your loop. So that's kind of a nice example, I would say. But yeah, in general, you go to the page and it's like, all right, stacks are a type of container adapter. It's adapting around something. It's not as its underlying thing, it's using what's called a deck rather than a list. But if you go to deck, we'll get to that eventually anyway. That is implemented most usually with a linked list. So it's lists deep down somewhere, if you want to think of it that way. Yeah, but technically all that you need to implement a stack is some type that you can mess with one of the ends of, and that's one of this. A deck is another ADT that we'll talk about. So yeah, so it's like, yeah, as long as I can do these things, that's what it's going to call in the underlying container. As long as it has an empty, a size, a back, a pushback, so it's going to the back. So hopefully it's using a different kind of list. But yeah, the standard container type classes, all these guys fulfill it, but deck is the default. So cool. Now we know. What else? You can go to the top, you can get the size of the stack, which is interesting. It's not really, I guess sometimes there's a need for that, but it's not. Some people don't consider that to be necessary for a stack ADT, but that is a thing that you can do. And also the top on stacks gives you back a reference to the thing. Gives you back a reference to the kind of thing that was put into the stack, your value type, that templated thing, whatever it was. So you can mess with the top, but that's all you get to look at and mess with. You can mess with it, but you cannot mess with anything below it until you start popping. So that's kind of neat. Yeah. Let's go there and make that example. So I'll just make a simple example of stacks, because you've seen them already. You've tried them. So I need the stack header there, and we'll just make a stack of ints. S, and I'll do this one. First I push 4, s dot push 4, then 2, then 42. Cool. And now I've got 42 on the top then, because that was the last thing that I pushed, and stacks are last in, first out, LIFO. The thing at the top right now is that, and I could have messed with it by saying s.top equals something, which is cool. And if I pop it, I'll be now with the top being the next to last thing. The 2 will be at the top there. So I can just keep on getting the top and popping it as long as it's not empty. And then it knows, so you could have done this in a loop, it knows that it's empty now, s.empty. And that will be a 1 for true now that I've popped all 3 things. So, good enough. Boop. So I've got my 42, that's the last thing, so it's in reverse order, right? I get the 42, then the 2, then the 4, and then now it is true for empty. Okay, so nothing really new. That's just one way to do it. You could have done this as a loop, though, like while it's not empty, keep on getting the top and calling pop. That could have worked, because eventually it would have become empty because you kept popping it. All right, so here is I don't know, I have one last silly question for you to try. Let's try this on the Written Ice page if you'd like. I'd like to hear your thoughts. So refresh the page if you're already on it. I'll clear it out. Here's my question for you. One thing that a stack kind of does for you is it does some sort of reversal, right? If I push 4, 2, then 42, I'm getting them off in reverse order, aren't I? Interesting. So maybe you could, I don't know, you could use this somehow to reverse a linked list. Let's say that somebody gives you a linked list. I'd like you to generate a copy, maybe, of the list and make this one. So don't actually write code for this. Try to write some pseudocode if you can. Just like in English, give me the steps that you would go through to like take in this list as a parameter and spit out this list as your returned value. Like how would you mess with this list, this original list, and then like copy it into this in reverse way, but using a stack. Remember that you can do pushing and popping and getting the top and stuff like that. So this is going to be very inefficient. Don't worry about that. I just want you to think about how you might use a stack to do this. Okay, does that make sense? Just try to write in English how you would take in this original list and produce the reverse list using a stack somehow. All right, and the stack operations that we've talked about. I'll give you a few minutes to discuss and write something down. So please just kind of say at a high level what you do. Like, all right, I'm going to iterate through this list, and this is what I'm going to do at each node. Something like that is what I wanted to see.
Until it's in the floating. Push to the back. It's about this to establish. To snap. I think so. Well, we want to finish making with that, so we're start pushing it. Well.
Another minute or so to come up with an idea. It's good to think about it in English sometimes. All right. Let's see what we're thinking. Like, how would you do? Like, I would probably start off my answer with my little recipe with, I'm going to iterate through the list, and at every node, I'm going to do the following. That's probably how I would start my little spiel. So push the first node on the stack. Yeah, well, keep on pushing the nodes that you're seeing as you're iterating through the list onto the stack. Good. That's the first step. Now you got everything on it, right, in opposite order. That's perfect. So while loop through the list, push it onto stack, and then while loop popping off the stack, right, to get it into your new list. Cool. So we thought of some ways. We even got some code. Very good. Thank you. I like that. I like those thoughts. So like, yeah, that would probably be what I do. Like, all right, I'm going to iterate through this list. At every time I see a node, I'm going to start a stack empty. I'm going to push the thing I see. Push the 1, push the 2, push the 3. As I see them, I iterate through the list. And then I'm good to start looping through the stack now, right? I can take the top thing. That's all I ever get. Take the top thing, pop it off, push to the back of a new list, kind of. Initially empty. Push back, pop. Push back, pop. Push back the top, pop. See how that would make 3, 2, 1? It's kind of inefficient, but who cares? That's cool. All right? That's fun. Any questions about this example? Highly encourage you to try it. You know how to make lists? Just make a C++ list type thing if you like. Iterate through it using a stack to create the reverse one and print out that new list to make sure that it was right. You can do all those things. That's great practice. All right. Yeah, my last example is kind of what we just talked about because we already had that question. But like a good example of a stack is like you go places in your web browser, like a back button kind of is a useful example of a stack. So like maybe you're looking at the documentation page for the C, or like you're going to Google or something like I want to know more about C++ stacks. Like that's your little query, and you press go, and then you see all these little articles with all the little links, and you're like, oh yeah, that one, that's what I want. Then you go to the C++ stack documentation page. If you think about it, all these things, like that's the next page you're on. Like you didn't open a tab or anything. Your back button is saving where you were, right? C++ stack. Oh, here are all the methods. Oh, I want to look at this method. Then you're like, oh, that was push. Let's look at the page for push and see its example and go from there. And then the second you press back, like you're here, right? Something like that. Technically, this is not fully correct because you could also go forward after that, but the sentiment is there, right? Like that's what your back button is good for. If I can draw a backwards arrow. Do, 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 do. Well, you go press that button. It's kind of, every time you go to a new link on the same window, it's kind of pushing where you were, right? First you were on Google, then you're on the C++ stack header file page, boop, and then you're on the page for push. And then if you press back, right, you go back to this page. It's like, kind of forgot about that. Maybe old browsers didn't have a forward button, I don't know. Then you pop that one, you're back to Google, you press back again. So that's another way you can think about stacks. Like it's useful because you can only kind of go back, or usually only want to go backwards. Who needs a forward button? Stuff like that. So you've seen plenty of examples of why you might want it. Though you can make it more complicated if you need to. So yeah, I think that's all that I wanted to say. So you've now seen some cool ideas, I think, for the day. It's one of the rare sets of slides where we can finish it all in one day. But I think that's all that I want to say about all these topics. And there's no assignments to release or anything because we got the midterm. Are there any last questions about anything before I just let you work? All right. That's all I got.